Hello, my name is Brendan Casbolt, and today I'm going to be explaining how to price um, commodity futures and basically the basic principles and how to price them, and the more advanced principles as well. I'm also going to be looking at different commodities such as oil and gold. Okay, so let's begin with the basic principles of futures and what a future is. So let's start with a forward. A forward is an agreement to either buy or sell a stock or commodity at a forward value or delivery value in the future. Futures are essentially forwards, except they are traded on a digital exchange. This makes futures default free. Now, forwards are actually traded between or over the counter pretty much. Unlike options, futures don't require a premium. Cash flow is paid at maturity. Okay, so let's start with the basic model of futures. So our future delivery price is the continuous compounded stock price at time t. So we see this is our delivery price at time t. This is our stock value at time t, and this is our time until maturity. So at t equals 0, we get this formula where it's our spot value at time 0, and our time remaining to maturity is just our maturity pretty much. Now, risk neutral valuation implies that the compounded future value of the current spot price has to equal the expected spot price at maturity, given the time up until time, given the information up until time t. And the reason why this has to hold true is if you think of it, if I sell you a stock, for example, then I can invest that money in a bank, and I can earn or that amount can grow to a continuous compounded risk-free amount in the future. So if that stock value doesn't have the same value of that in the future, then this would call for a mispricing and would open an opportunity for arbitrage, risk-free arbitrage, or in other words, a risk-free profit. Commodities. So commodities are raw materials that can be bought and sold. So example, we have gold, oil, soybeans, cotton. Now today we will actually be describing gold and oil. Commodities are traded on exchanges via futures contracts. Now this is interesting because in real life, consumption commodities don't actually have a physical spot price. They've actually got just the future price listed on the market. So this is something that we'll explore later on. Now we have two types of commodities. We have investment, which is say gold, silver, platinum; consumption, oil, soybeans. Commodities may be classified according to their supply, demand, and holding benefits. Okay, so let's have a look at investment commodities to begin with. Consider gold as an example. So investors who borrow gold from producers, for example, mining companies, for example, are required to pay an interest rate. Well, it's actually called a gold lease rate. And so let's have a look at our basic model to begin with. So if you're continuously paying that rate, then our future value will be equal to this value here. However, this is actually incomplete. And now the reason why it comes down to arbitrage. Gold producers are actually required to store commodity in inventory. Thus, to negate arbitrage, borrowing gold requires storage costs. Now, if you think of it, if we don't include storage costs that the short holder has to pay over that time period, then this will benefit the long holder, because what this means that our future price will be overpriced, and our long holders will be able to exploit arbitrage from this opportunity. So we have to include our U or our storage cost in our formula. So this is our investment commodity formula. Consumption commodities are usually commodities that can be invested and or consumed that's in real life. They too require storage costs. So let's begin with the following. So let's start with the basic storage model of futures. Now this is also incomplete. Consumption commodities are consumable. So this means a short holder may utilize the commodity over the delivery period T to their benefit and make cash flow. This means our futures model is in current form would actually be underpriced, and so in this case here it would actually benefit the short holder if we do not include some sort of other convenience yield into this model, which we will get to in the next slide. Now, an example of a consumption commodity that we're looking at is oil. Generally exhibits seasonal fluctuations in supply and demand. As a result, when prices boom, the holder could be at an advantage. That's if we don't come to the next model in the next slide. So convenience yield is the cash flow of direct benefit from holding the consumption commodity to the short holder, denoted by Y. This needs to be subtracted from our investment model to negate arbitrage. So we end up with this model here. Now, if our U and our Y are actually proportional to our spot price at time zero, or actually no, sorry, if our convenience yields and our storage costs are proportional to our spot price at time zero, then we can actually factor them in as a rate and continuously compound them against the spot price over time up until maturity. So we end up with this model here. Okay. So let's go to the next slide. The physical spot price of commodities. So let's have a look at problems with this model. So the problem with this model is that spot prices such as oil spot prices are unobservable, and prices are actually just listed in the future market. So the thing is, the spot price listed in the market is actually just a proxy, a proxy of the closest future price with maturity. So it's not actually the physical spot price, it's just a proxy. So this makes it difficult for us to actually, to price futures, we have to figure out what our spot price is. And this is difficult because we don't actually know what it is. Because of this, also convenience yields are unobservable. Because if we don't know our spot price, then how can we work out our convenience yield by using our future price and our spot price? That's not possible. The next thing we have is convenience yields are non-deterministic. Okay, the constant convenience yield model assumes that volatility of futures contracts is identical to the spot price. Now, empirical data actually shows that the volatility decreases with maturity. So it's actually changing. So the volatility changes as we approach maturity. So this implies that there has to be some sort of stochastic nature within the convenience yield. Thus, the convenience yield has to be changing over time, which makes things interesting. Okay, so the stochastic futures model. So we're going to assume that our convenience yield and our spot prices are non-observable. They also follow a stochastic random walk. The futures contract with the closest maturity, as I explained before, is used as a proxy for the spot price. Now, we actually define convenience yield over here differently. In our other slide, our convenience yield was just this benefit of direct access. But instead, we're accompanying the whole thing, including the cost of storage as well. So this was our Y. Sorry, that's Y. Oh, sorry, let's rub that out. So this is our Y. This was our U. Okay, so what this says to me is that convenience yield is actually a very complicated quantity to categorize. And these two benefits of direct access and cost of storage they must be related in some way, stochastically speaking. And it's probably better off just looking at examining just the one whole quantity. We can probably get like a better picture from just looking at just this convenience yield defined this way. Okay, so this is our new model. This is what it looks like. Now, we're also going to assume that this is R is deterministic. Okay. Next, we have the concept of mean reversion. So it is assumed that changing price in futures contracts moves closer to and oscillates around a mean price as T approaches maturity. Now, the reason why this is so is because as the future prices become more expensive, this draws in people who can afford higher storage costs into the market, which will push downward pressure or force the prices to move down. Now, the opposite happens. If the prices are low, then investors who can afford higher storage costs, they actually opt out of the market, which pushes us up. And now this is actually interesting, because what I'm wondering is there some sort of critical ratio between our benefit of direct access and our cost of storage that will either push the market up or down? So this is something interesting that could be looked at. I'm not really sure whether it has been looked at. And what would it mean in a stochastic sense? So that's something else to look at. Next, we look at a commonly used model called the Gibson-Schwarz 97 model. So this model's two factors, and they're both stochastic. So we have our spot price and our convenience yield. So delta is our convenience yield, S is our spot price. Okay, and they're both random walk models. They actually have a special name. I haven't actually listed it down. I think it's like an Ornstein process or something. I'm not really sure. Okay, so equation 1 assumes logarithmic stock price, with R being the constant interest rate. Okay, so it's deterministic. Equation 2 describes the motion of the convenience yield. So this part here is actually our mean reversion part. Now, what would happen is if we were to ignore in equation 2, if we were to say ignore this bit here and integrate this bit here and take the limit as as t approaches t, we would see that our function will approach. It will actually approach alpha as but because we have this stochastic component here, it will just get closer. It will actually just get closer to alpha. It won't actually approach it. So it reverts. Okay, so solution. So Upon inspection, taking the log spot price and using Ito's lemma to find its distribution, you see it includes this in the drift term. However, this is stochastic, so this means the mean would always be changing. Therefore, it doesn't really have a distribution, or there is no distribution for the log spot price. We haven't got any definition of what it would be. So now let's solve under risk neutral valuation. So our risk adjusted drift is going to be R minus delta. And the reason why we use R is because it's risk neutral. We don't use the mean. We use the risk-free interest rate. And our adjusted convenience yield is now kappa alpha minus delta t minus lambda. Now this lambda is a market price of the convenience yield risk. So it's actually the excess premium that needs to be considered within taking the risk. I think that's what it means. Yeah, I'm not 100% sure what that means, but I have a vague idea of what it means. Okay, so we can rewrite our equations like this: 4, 5, and 6, and then we solve. So we express our future. So this is our future as a Taylor expansion in terms of delta and S to obtain the following PDE, and then we solve it according to these boundary conditions, right? And as you'll see in the next slide, we obtain an analytic solution. So this is our analytic solution. Now, because our parameters, our spot price, delta, or convenience yield, alpha, kappa, and rho are all unobservable, we need to estimate them. And the way we estimate them is by generating a regression of past future prices, which is done using a Kalman filter. Now, I'm not going to go into detail about this because I haven't got enough time to explain how it works. Okay, and other things we can include is seasonality. Now, if we consider crude oil, for example, so prices tend to rise in summer driving season, where in the US, for example, as we see in this graph down here, we see that they peak mid-September and October. So over here is a peak. Now, they also tend to fall during early October due to sluggish demand in winter. So obviously, in warmer seasons, there's a higher consumption rate of oil, which leads to higher prices. In winter, there's less consumption, which means the prices drop. So this produces a seasonal effect. Okay. So to account for seasonality of prices, we include a seasonality factor. So this is like a Fourier series. And we can include this in our convenience yield or our spot price. Now, there are models that actually integrate this factor better than others. I think the Schwartz Smith, it actually defines the factors differently, the stochastic factors, and it incorporates seasonality a bit better. And I've seen in many research papers that they use the Schwartz-Smith model to model seasonality more so than the Schwartz-Gibson model. So investment commodities like gold don't really require seasonality components. Okay, improving accuracy of the model. Accuracy just depends on how well the model fits data. Okay, so we can add extra factors to the model. This may or may not improve the accuracy. And it really depends on market conditions at the time. Now, for example, the three-factor model adds another stochastic quantity for long-term average or moving average. Other things that we can look at is synchronistic behaviors of commodities. I mean, is there a correlation between price fluctuations between commodities such as oil and natural gas? And can we sort of use this to determine or to better model our futures. Okay, and here's my references, and that's essentially the end of my video presentation. Thank you for listening, and thank you for granting me the extra time to complete this assignment. It was actually quite interesting and challenging.